So last lecture we talked about the Kramer-Rao lower bound, and we talked about how we can use that to find the UMBUE, our best estimator. And today we're going to talk about, we're going to show some proofs of this Kramer-Rao lower bound, and we're going to talk about in which cases we know that we can use this Kramer-Rao lower bound to find the UMBUE, the best estimator. So let's do a real quick summary of the Kramer-Rao lower bound theorem. So let's say theorem, Kramer-Rao lower bound. And the theorem can be pretty succinctly summarized, which is that if theta hat is an unbiased estimator of some function of our unknown parameter, tau of theta, then the variance of our estimate of tau of theta, the variance of theta hat, can never be smaller than d tau d theta quantity squared divided by the information contained in our sample about theta. And there is a kind of asterisk here, which is that this is true if the PDF of our data, f theta, is regular enough. And basically, for one-dimensional parameters, for just some number theta, this is going to pretty much coincide with situations where it will work for one-parameter exponential families, and will not work for distributions or families of distributions where the support of the distribution depends on the unknown parameter theta. So that's, in a nutshell, the Kramer-Rao lower bound. Let's actually start off this lecture by looking at a proof of it. We saw last time how it can be used, and let's actually write out a proof. The proof is not too bad. The proof relies on a couple facts about correlation. So if I have two random variables, A and B, the correlation between A and B is defined as the covariance between A and B divided by the square root of the variances. Square root of the variance of A, times the variance of B. Here, covariance between two random variables can kind of equivalently be defined to be the expected value of the product minus the product of the expected values. So this is our shortcut formula for covariance. There's a kind of more formal definition. Formal definition of covariance is A minus its expectation times B minus its expectation. Basically, I mean center A and B, and then I take the expectation of their product. So this is just some basic facts about correlation. The second basic fact about correlation, which I proved when I teach 451, I typically do a little proof of this. The correlation between two random variables always is going to be restricted to be between plus and minus 1. The follow-on fact of this is that if the correlation has to be between -1 and 1, then if I square my correlation, this is strictly less than 1. It's positive, right? Squares are always positive, and it cannot be in magnitude. Oops. if I square it, it cannot be bigger than 1. So these are some basic facts about correlation. And notice that if I rearrange, let's call this fact 1 and this fact 2, is that I can combine these facts, and let's say combine 1 and 2, and I get the fact that the correlation, the covariance between A and B squared divided by the variances, so just squaring this above formula right here, that is a correlation, that thing is less than or equal to 1. So we have this less than or equal to sign, which is good, right? This is going to end up at the end of my theorem being this less than or equal to sign. So we're making some progress, and I can rearrange and I'm going to rearrange by moving, doesn't matter, pick A or B, over to the other side. Let's say this says that the variance of A is greater than or equal to, so I'm just going to multiply both sides. The variance of A is greater than or equal to the covariance of A, B squared divided by the variance of B. So this is looking pretty familiar at this point. If we go back up to our Kramer-Rao theorem, it's the variance of theta hat is bigger than or equal to something squared divided by something else. And what we have at this point is the variance of A is bigger than something squared over something else. So to show, or let's say to prove theorem, what do our constituent A's and B's have to be? Well, that A is basically playing the role of theta up here. So let's say let A be, theta hat, and the information is in my denominator. Well, my denominator of this is the variance of some quantity B. And what quantity, when I take the variance of it, gives me my information, that is going to be my score. So if I let theta hat be A and B be my score, all I have to do is show this dot part is that derivative squared, and everything works out. So let's show some facts. What we can first show is that 1, we know that the variance of the score is defined to be my Fisher information. All right, so that's our definition of the score. There are fancy ways to calculate it, but this definition of the variance of the score. There are fancy or not fancy ways to calculate this, but that's what it is. And 2, all I need to show is that this covariance of A and B gives me this derivative, and then my square comes along, right? So we need to show that if I look at the covariance between theta hat and the score, so these are both random variables based on the sample. Theta hat is a statistic based on the sample. The score is some other statistic. It's based on the sample. It has some fancy formula, but it's just another random variable based on my sample. We need, if we can show that this thing is the derivative of d tau d theta, everything's done. Then A would be placed with theta hat, the basement here would be placed with the information, and the top would be placed with that square of that derivative. So if we can show this, we're good. So let's show it. So the covariance between theta hat and the score is by my shortcut formula. So if we go back up to our shortcut formula here, the covariance is expectation of the product minus the product of the expectations. So expectation of the product is theta hat times the score. And then I subtract off the product of the expectations, the expectation of theta hat times the expected value of the score. Nicely, and I'm going to put a little asterisk here, as long as our PDF, our f theta, has enough regularity, we know that the expected value of the score is 0. And so this whole thing, this whole second term, is going to go to 0, which leaves us just with the expected value of the product of theta hat times the score. Now, I have no intuition about that. I wouldn't have come up with this theorem, but we can actually look at what this thing is. And so the expected value is just the product of two random variables. It's expected value of theta hat times s theta, and then we integrate against the PDF. F theta of x dx. So something like that. Now we should remember what our score function is. So let's write this to the side here. We'll say recall this fact. And the fact to recall is that s theta, our score, is, of course, d theta of log f theta evaluated at a random variable. And d theta of log f theta is, well, the derivative of the log of a function by the chain rule. This would be, well, let's write it this way, d theta of f theta divided by f theta. So we can add our little x's here if we want to. What this means is that when I'm writing out this integral, I can replace s theta with this expression. So this would be the integral theta hat. Now in place of the score, I'm going to put d theta of f theta of x divided by f theta of x times f theta of x, which I bring down from up top, and I'm integrating against all my x's. So notice here nicely that we get some cancellation, right? The f theta on top cancels with the f theta on bottom, and we get the integral of theta hat times the derivative of f theta of x with respect to theta. Now, theta hat does not depend on theta, right? By definition, theta hat is a statistic. It can't depend on an unknown parameter. And so as far as the derivative with respect to theta, theta hat is a constant. It can go in the derivative, come out of the derivative. And so if we have enough regularity, I'll put a star here, just remember, if we have enough regularity, maybe I should put a star in the next step. What we can do is we can bring that derivative outside. And we can write it like this, where it is d theta. We'll bring that outside the integral. So it's the derivative with respect to theta of the integral of theta hat times f theta dx. Now, this integral is exactly the expected value of theta hat, right? is the integral of theta of x. You can remind yourself that's a function of x times the PDF. You integrate that. That's exactly the expected value of theta hat. And we have a name for that. We were calling that in our theorem. We called that tau of theta. If we go back up to our theorem here, tau of theta is the expected value of theta hat. This theta hat's unbiased for tau of theta. And so what we get here is that this is d theta of tau of theta, which of course you could write as d tau d theta, for example. So this basically completes the proof. Let's bring all the parts together here. Because what this showed is the last piece we needed, which is that the covariance between theta hat and the score is d tau d theta. So we use this inequality here, let's rewrite it, is that for any random variables, a and b, the variance of a is always going to be bigger than the covariance between a and b quantity squared over the variance of b. With careful choices, if we let a be our estimator, theta hat, and we let b be our score, then with these kind of careful choices, we have shown, or we know, that the covariance between theta hat and the score is d tau d theta. We know that the variance of the score is, by definition, in some sense, the information, and variance of a is just the variance of our estimator. So if we can plug all these in, we get variance of theta hat is the covariance between theta hat and s squared over variance of the score, which is the information. So that's the theorem, and that's the full proof. So, you know, it's not so bad of a proof that you can't do it. It's actually quite nice. It relies on facts and several points, the regularity of f theta, that we can interchange differentiation and integration. So it relies on that fact being true. Practically, for this course, what that means is that this theorem will work for exponential families, and it won't work when the underlying PDF depends on, the support of that PDF depends on any unknown parameters. So we've talked about this, and last time we spent quite a bit of time discussing how we could use this theorem to find the best estimator. And we had said, and we had done a whole bunch of examples last time, that if I have theta hat and is unbiased for whatever function of my parameter I want to estimate, and I can show that the variance of this thing by some calculation is equal to my bound, Cramer lower bound, which is d tau d theta quantity squared divided by the information. So basically I had to calculate the square of the derivative, and I had to calculate this information. And if I could show that, then theta hat is the UMBUE for this function of this parameter that I want to estimate. Because the thought being is that if the variance of the thing achieves the bound, there cannot possibly be an estimator with a lower variance. We also made a second point, which is that, however, spell however correctly, if all I can show, or all I know, is that the variance of my theta hat is somehow bigger, but not equal to, but it's bigger than the Cramer-Rao lower bound. I don't really know. I don't know if theta hat is the UMBUE, right? The reason being is that I can't prove it's the UMBUE just from using this theorem, because I don't know if there's an estimator, some other estimator that sits as a lower variance than theta hat, that, but you know, it has to respect the lower bound by the theorem, but it might have a lower variance of theta hat, a lower variance than theta hat. So there might be something between these two. We don't know. On the other hand, we don't know something like that exists. So we don't know this thing definitely isn't the UMBUE, right? All the theorem says is that this bound exists. If you can show it achieves the bound, yeah, it has to be. But if you find something and it is bigger than this bound, possibly there's something between them. Possibly there isn't. Possibly there's nothing, and just no estimator achieves the Cramer-Rao lower bound, and the best estimator achieves some higher bound. So this bound is not tight. The bound isn't always tight. And by that, I mean sometimes nothing ever achieves it. Sometimes nothing achieves the Cramer-Rao lower bound. So this is going to spur the discussion for the rest of the lecture and into the next lecture, which is basically, first of all, how can we tell when we're going to get a situation where it does achieve the bound? Is there something we know in advance that can help us with this, rather than having to derive the bound every time? And secondly, is there another way of finding the best estimator? And so the first question we'll answer today, and we will start down the road of answering the second question today also, hopefully. So here's the theorem. I'm going to write the theorem up out front, and we'll look at an example, we'll look at a proof, we'll look at an example. So here's the theorem. If my favorite setup, I have my data, comes from some distribution with an unknown parameter, and f theta satisfies the Cramer-Rao lower bound theorem conditions, which basically means it's regular enough for everything to work out nicely. And we have theta hat, let me just say this in good English, and theta hat is unbiased for some function of our parameter we want to estimate. Then theta hat achieves the CRLB if and only if the following is true: the score is proportional to theta hat minus tau of theta. So let's parse that a little bit. First of all, this symbol is read as proportional to, which means that it might not be exactly equal to be up to a constant. So sometimes people add on a little theta here. Up to a constant that potentially depends on theta. but doesn't depend on theta hat or depend on tau, I guess. It doesn't depend on theta hat. Up to some function of theta, they're equal. So what this means is that, i.e., the score is some function of theta times theta hat minus tau of theta, where this is some function. I don't really care what it is, but there's some function that potentially involves theta. It doesn't have to. It cannot involve theta hat. It cannot involve the x's. So let me write that. Some function of theta, not the x's. If there's some function of that such that the score is some function involving theta, not the x's, times theta hat minus tau, then theta hat achieves the CRLB, hence theta hat is the UMBUE for tau theta. So, so this is kind of a nice little theorem. Notice you only have to calculate the score. You don't actually have to find the information. You don't actually have to calculate the variance of our estimator. All you have to do is calculate this score. And if you can somehow factor it into something that depends on theta, which we don't really care about, but in there, the only way that theta hat appears basically is in this kind of relation where it's theta hat minus tau, and then there's some, maybe that's multiplied by something, but whatever, then theta hat is the UMBUE. Super useful example. Let's look at an example just to make this a lot more concrete. So let's say our data comes from Bernoulli, some Bernoulli distribution, depending on some parameter p. And what do we want to call it? Not theta hat, let's call it p hat, be x bar. That's what we'd call in intro stats, right? P hat is x bar. And tau of p would be, let's just call it p. So tau is the identity function. Then p hat is unbiased for tau of p, right? Why is that true? Expected value of x bar is p, right? So we're all good. So this is an unbiased estimator. Is this the UMBUE? I don't think we've done this one before. So let's do it. What do we need to do? We got to form the score function, right? And so the score is a random variable, depends on our data, but it's what? d theta of log f theta of x, right? And so this f theta here, which I've used in notation sometimes, this is their joint distribution, okay? And so first, let's figure out what f theta is. Take its log, take a derivative of it, right? So not too bad, right? So f theta of x is the joint, which is the product of the marginals. Each of them are marginally Bernoulli. The PDF for Bernoulli can be written as p to the xn times 1 minus p to the n minus xn. That is one way of writing the PDF of a Bernoulli. Again, I'm going to ignore the indicator function on it. It doesn't depend on the unknown parameter. It's going to go away when we take a derivative, so no big deal. And so that's f theta, log f theta, is so the product turns into a sum, right? This is kind of how logs work. Products turn into sums, and then we push the log through. And so we're going to push the log through to the inner part here. it's in the log of, well, let me just write it out. I'll do it in a couple steps. Okay, something like that, right? And then we can distribute this log. The xn comes down. We get a log p. The product becomes a sum. Let's put some brackets around this whole thing. Sum. And the n minus xn comes down. By the end of this class, you'll be an expert at manipulating logarithms, is the one real skill you'll retain from this. And then we get a log 1 minus p. Okay, close that, and then we can distribute our sum through. Yeah, doesn't really matter what order we do this in. Let's distribute it through. Or equivalently, you can think about pulling out this log. So it's, let's say it's log p times the sum of my x of n's plus log 1 minus p. And of course, you can't correct me. That should not be an n, it should be a 1. I'm sure someone's been really confused. Sorry, that should be a 1. Bernoulli, that should be a 1. And then I get the sum of 1 minus xn's, which we can write as this thing is n minus the sum of the xn's. Okay. And now we want d theta of log, we'll get there eventually, of log f theta of, let's write a deterministic x, something like that. Derivative with respect to theta, of course, we're not talking about theta, we're talking about p in this case. Derivative of log of p is 1 over p. Derivative of log of 1 minus p by the chain rules is negative 1 over 1 minus p. You can check my math on that. That should be chain rule. And then I get an n minus something like that. Now, I really don't want to have to write these sums a bunch of times. Notice that the sum of xn's is the same thing as n times x bar. So I can replace these with n times x bar. And that will make me happier because I don't have to write sum of x, the sigma notation a bunch of times. So what I get is n x bar over p minus n times 1 minus x bar for 1 minus p. And I want to simplify this more, so let's cross multiply. This is 1 minus p times n x bar minus p n times 1 minus x bar over p by 1 minus p. And just a bunch of algebra here, nothing too bad. N x bar minus p n x bar minus pn plus pn x bar all over p by 1 minus p. Whew. Okay. There, once we get to that, now we get some cancellations. In particular, we get that. And so altogether, we'll have an nx bar and a pnx bar, or a pn up front. I can factor out that n, and I'm going to write this in this fashion. Believe me, that is equivalent. Why did I write it that way? What were we actually calculating at the end of the day? We were calculating the score, s theta, right? If we scroll back up, that's what we were calculating. And the theorem says we want to write the score as some function involving the unknown parameter times the estimator minus whatever the mean of the estimator is. And so what I've done here is this is what I was calling a of theta. And then we get theta hat, oh boy, let's call it a of p, and then we get p hat minus tau of p. So by our theorem, What does the theorem say? Well, on its face, the theorem says that if and only if this thing is true, which we just showed is true, this kind of proportionality, theta hat achieves the Kramer-Rao lower bound, and therefore it is the UMBUE. And so in our case, by our theorem, p hat is the UMBUE for p, let's say. So if I get Bernoulli data and I want to estimate the proportion p, the best I can do is x bar, or what I'm calling p hat here. So that's a nice little example. And it's got to be quicker than calculating the information, I would assume, because you already have to have the score. Maybe not, but it's at least an alternative way to check your gut here. And yeah, I don't know which is going to be easier, but it definitely is an alternative way, and it shows us that it's a nice little theorem. And in this case, it tells us that this is the UMBUE for estimating p. So let's actually look at a proof of this theorem. We can maybe look at some more examples. Yeah, and then we'll relate it to exponential families. But the theorem here says that basically I need to write my score as sum a of theta times theta hat minus tau of theta. Okay. Now, let's go back and look at our proof of the Kramer-Rao lower bound, because this is going to help us out, right? So we had the statement that, let me scroll down here, right? Here's basically the sketch of the Kramer-Rao lower bound proof. And so we had the variance of A is bigger than or equal to the covariance squared over the variance of B. And notice that, let's just rewrite it, right? So back down here. So let's say from proof of CRLB, let's just say that the variance, what we had basically shown is that the variance of theta hat is bigger than or equal to the covariance between theta hat and our score over the variance of our score. Now, this can be greater than or equal to, right? It's a greater than or equal to sign. And the theorem that we want to prove now is about when it's equal. So we want to prove when equal. So we want to prove that case. And so we want, let's just say, what we want is that we want the variance of theta hat to be equal to covariance of theta hat and the score over the variance of the score, right? That would be the case where our theta hat achieves the CRLB. And we can rewrite, if you remember, we had derived this inequality up here, generally for any A and B, by looking at just the variance, looking at the correlation. And so we can move this variance of theta hat to the other side. What we want is the covariance of theta hat and S theta over the variance of S theta times the variance of theta hat. If I just move this theta hat to the other side, we want that to be equal to 1. And we'll notice that if you go back to the previous theorem, how had we derived that thing? We had looked at the correlation way back up to here. We had looked at this correlation, and that is ultimately by rearranging that, we had rearranged it into this inequality. And so this was equivalent to saying that this was the correlation, right? Or the squared correlation. It's always less than or equal to 1. So by undoing that rearrangement, which is basically what we're going to do here, this is, however you want to recognize it, this is the squared correlation between between theta hat and s theta, right? And I'm saying if my theta hat achieves the Cramer-Rao lower bound, this squared correlation must be equal to 1, right? This is the Cramer-Rao lower bound, and written in another form, we want it to be equal, not greater than, which means that this whole thing has to be equal to 1 upon rearrangement, and that is the squared correlation. And if the square of something is 1, and it's positive, I guess it doesn't even matter. If the square of this thing is 1, the correlation between theta hat and s theta is equal to plus or minus 1, right? So the square of something is 1. The correlation between theta hat and s theta better be either plus 1 or minus 1. We don't really know the sign. What this means is that, and I don't know if we proved this in 451. It might be a little beyond the scope there, but people will believe me that the things are perfectly positively or negatively correlated if and only if they are linear functions of each other. So what this means is that theta hat and s theta are linear functions of each other. Right? If the correlation between two things is perfectly exactly 1 or negative 1, they have to perfectly be linearly related. So what this means is that we could write, I don't know, the score as some function, let's call it, or some a plus, let's write it this way, is some b plus a times theta hat. You might recognize a from before. Yes, that a. So there's some linear relationship, some intercept b and some slope a. If the correlation has to be plus or minus 1. And here again, we have to use our favorite word here, which is recall that in expectation, the score is 0. So, of course, the expected value of the score is, if it, in this case, is perfectly linearly related, if we achieve the Cramer-Rao, it's perfectly linearly related to theta, then this would just be expected value of the score is b plus a theta hat, and of course that has to be 0. And the expected value of b plus a theta hat is b plus a expected value of theta hat. All right, and we call expected value of theta hat, we had a name for that, that was tau of theta, which means that what I can solve for, I don't have 2 degrees of freedom to choose both a and b. One is going to be decided by the other, because there's this whole thing must, in expectation, be 0. So let's just solve for b. B must be negative a times tau of theta. So if I bring that back down with this fact, s theta is b. So s theta is b, which we know is negative a tau theta, plus a theta hat. We could, of course, rewrite this as some a times theta hat minus tau theta. That's the proof, right? This a could depend on theta. You don't have to. It doesn't have to, but it could. It will not depend on the x's. But so what we did, right? So let's just do a quick recap, right? The theorem says that we know some theta hat achieves the Cramer-Rao lower bound if and only if the score is some a is proportional to the theta minus tau theta. There's some a times theta hat minus tau theta. And we basically proved that by, again, rearranging that proof of the Cramer-Rao lower bound and showing that if it achieves the Cramer-Rao lower bound, basically that means that the score is linearly related to the theta hat. And we could exploit the fact that the score has expectation 0, and you could write it in that form. So that's kind of cute. What this says is that the score is proportional to the difference between these things. let's look at another example. And we actually, we did this one last time, but let's just do it again. Our favorite distribution, a normal distribution, and let's assume that sigma squared is known. So the only unknown parameter is going to be our mean mu. And so let's again, in a different way now, show that we had seen that if we let mu hat be x bar, then certainly the expected value of mu hat was mu, so it's unbiased for mu. And we had shown last time that it did actually, we actually had calculated the variance of this thing. We showed it achieved the Kramer route lower bound. Another route you could use to show that, kind of a theoretical tool you have in your tool belt, is that you could use this kind of proportionality theorem. So what you would do is you would form the log likelihood. Well, let's just do it, right? Or the score more generally, right? So let's just go through our little steps here, right? So our score, f of x's was, probably done this a million times. I'm going to do it a little bit fast, right? The joint distribution is a product of the marginals. Each marginal is normally distributed, 1 over root 2 pi sigma squared, exponential, -1/2 sigma squared, xn minus mu, quantity squared. We can push this out. This is 2 pi to the -n/2 sigma squared to the -n, exponential, -1/2 sigma squared. And we can push this sum, this product can get pushed into the sum, do a sum with an exponential, and it looks something like that. So did that quite fast, but I've done that calculation a couple times. So if you need to pause it and work through that, right? Which means log of f theta, or f of x, is -n/2 log 2 pi minus, of course there's over 2, I forgot, it should be n/2 log sigma squared minus everything, the exponential just comes down, 2 sigma squared, sum, xn minus mu, quantity squared, okay. And then we want derivative with respect to the unknown parameter, in this case that's mu. -n/2 log 2 pi theta does not depend on mu. -n/2 log sigma squared does not depend on mu. That also goes away. What do we get? We get a negative. The 2 will come down, we cancel this 2, and we'll go negative from this mu. That will cancel with that. I think I've done this a couple times. I think all we're going to be left with is a 1 over sigma squared. But you can check my work on that, right? So this is basically my score, right? S, let's say of mu, I guess, is basically this, but I replace my deterministic x with the random x, right? So 1 over sigma squared, right? And say 1 over sigma squared. This is, we can write this as nx bar minus n mu. So what I get is n over sigma squared, x bar minus mu. And so by my theorem, I found some a of mu. Now in this case, it doesn't depend on mu at all. It doesn't have to always. And then I get my mu hat minus mu. Let me write it down here. And so, as we showed last time, x bar is the UMBUE for mu. So if you didn't believe the first time, you won't believe the second time, but I'll do it again. So, that by that theorem, because we've shown that proportionality mu hat, or x bar, is the UMBUE. Shall we do another example? I think more examples are usually good, right? What did we show last time? We looked at the exponential distribution. That's another thing we could look at. So let's say example. From an exponential distribution with some rate parameter lambda. In this case, let me actually write out. What was my UMBUE? What do we want to call it? Lambda hat be x bar and tau of lambda be 1 over lambda, right? Then let's look at this, right? So this thing, this is the joint, is the product of marginals. Each of them are exponentially distributed marginally. Distribution is negative lambda e to the negative lambda x sub n. I'll ignore the indicator function because it does not depend on my unknown parameter. It's going to go away when I take a derivative. It don't matter. I can push this product through. That's lambda to the n. I think I've done this about a million times. People are probably bored. And this is what I'll get. It's good practice, manipulating these things. So log of f lambda of x is, I get n log lambda. Product becomes the sum minus whatever is in my exponent. Whenever you see the sum of the x sub n's, you should always recognize that that could be written as n x bar. That's cute because x bar shows up there. Well, that's promising. So this thing you could write as n log lambda minus lambda n x bar. And d lambda of log of my joint, supposed to read log, is derivative of log lambda is n over lambda, and this just becomes n x bar, right? So my score, which depends on my unknown parameter lambda, is n over lambda minus n x bar, which again, pretty simply, I think if I take out a negative n out front, I'll get x bar minus 1 over lambda. And Bob's your uncle, this is how it works. This is a of lambda, doesn't actually depend on lambda. This is lambda hat, and this is what we're calling tau of lambda, or maybe we didn't call it that, but you could. Yeah, we did call it that, right? So x bar is the UMBUE for 1 over lambda. So it is important to make sure that's correct there, that this is, it's not the UMBUE for lambda. It's not even unbiased, right? UMBUE, you don't want to lose sight of what that actually means. The minimum variance, uniformly, minimum variance, unbiased estimator. X bar is unbiased for 1 over lambda. It ain't unbiased for lambda. It's not the UMBUE for lambda. It's the UMBUE for 1 over lambda. What is the UMBUE for lambda? It's a great question. And next time we're going to get into that, because this procedure so far with the Kramer round lower bounds has allowed us to find certain things. But what if I have a more complicated tau of lambda? I chose my tau of lambda so far to conveniently work out to what I want. And it may not always be that nice. What if I want some more complicated function? So we'll start getting into that next time. Okay, so to wrap this all up, we're going to bring this back to our favorite set of family of distributions. And we'll write a theorem that says, maybe we'll call it attainment for exponential families. Attainment for exponential fams. So let's say, I have my data. It's a random sample from some f theta, and f theta is an exponential family. And what does that mean? It means that we can write our joint distribution, f theta of x, as some function involving just the parameter theta, some function, and not the x, some function, so we can write the joint as some function involving the parameter, not x, times some function involving x and not parameter, times exponential, hence the name, of the product of similar things. Something involving the parameter, not x, times something involving x and not the parameter. So it turns out the punchline of the theorem is that this t of x, which is a statistic, it's a function of x, is the UMBUE for its expectation. What do I mean by that? Let's just call tau of theta whatever the expected value of t is here. All right. So we're just going to say we want to estimate whatever t is unbiased for. Then t is the UMBUE for tau of theta. So what this does is that if you give me an exponential family, and so I can recognize the parts, so I ask you, okay, is this an exponential family? Is this an exponential family? You recognize the parts or you don't. And so I recognize the t part of this exponential family. And I say, okay, the t is unbiased for only one quantity, whatever its expectation is. And I say, okay, so t is unbiased for something, theta squared, e to the theta, hyperbolic tangent of theta, whatever it is. It's unbiased for something. It is the UMBUE for whatever it is unbiased for. So it's an unbiased estimator. Every statistic is an unbiased estimator for its expectation, definitionally. It's always unbiased for its own expectation, because all unbiased means is that it has that as its expectation. It's kind of circular. And so if you were interested in estimating that particular quantity, the best way to do it for a one parameter exponential family is to use t. So it brings it back to our kind of really nice family, kind of nice distributions, these exponential family distributions. If you happen to want something for tau of theta, use t. And that is, the dirty trick here with all the examples I've been giving. I've just been choosing tau of theta. If you go back, this is exactly what I've been choosing, right? So this tau of theta is what we're calling, or this tau of lambda in that case is what we're calling w here. It's exactly what we're choosing. And, so that's true. Sorry, it's not what you call w of lambda. It's what the expectation of tau is. It's true of this normal example. It's true of the Bernoulli. It's true of this exponential. It's true of it's even true of the Poisson example we looked at last time. So a little bit of a cheat, but not too much. Sometimes those are super useful things. Like in the normal distribution, estimating the mean is typically what we want to do. And so it is actually nice that works out. So again, what I like about this kind of theory is that the proofs are accessible at this level. They take a little bit of thinking, but they're not too bad. It's not like we need to bring in complicated topics in analysis here. So let's look at the proof. And this proof is going to use the previous theorem that we proved, that proportionality theorem, right? And so, okay, let's look at it. If this is f theta, then log of f theta of x, let's say, note that log of f theta of x, we're just going to take the log of this, is log of c theta plus log of h of x plus w theta times t of x, right? And so if I take a derivative of that with respect to theta, what do I get? Log of, by chain rule, log of some function of the variable I'm differentiating against is let's call it c prime of theta over c of theta. Now that's just chain rule with logarithms. H doesn't depend on theta, so this whole thing goes away. And then we have a w prime, whatever the derivative of w is with respect to theta, and this t doesn't depend on theta, it just comes along as an extra constant, right? So this thing is basically my score, right? Of course, really for a score, this x has to be treated as random. So my score is basically c prime theta over c of theta plus w prime theta times t of x, all right? Something like that, all right? And so this is looking kind of promising. What do I want to do? I want to write this as something t, right? I want to show that t is the UMB for tau of theta. And so we can do that. What are we going to do? We're going to say, what do we want to factor out? Let's factor out w prime of theta. If we factor that out, we can have t of x, and then we're going to have we want to write this as minus something. So let's say minus. Okay. I believe those two things should be equal, right? If I have if I cancel my negatives here, so I have negative, negative, that will give me, and then I multiply by w prime theta, that will give me the above line. And so if I were to call this tau of theta, what I would get is that w prime theta times t minus tau of theta. My score is proportional, all right? You can call that w prime of theta, you can call it a of theta. It's proportional to my statistic minus what I'm trying to estimate. And so that would show that t is the UMB for tau of theta. Now, I may just go sleight of hand here, maybe someone to call me on it, where I call this thing tau of theta. Now, I could just name this kind of mess of c's and primes and negatives and thetas and w's and primes. I could just call it tau of theta. But I have to be careful because I said that t is unbiased for a tau of theta. And I never actually established that. All I've established is that I can write, up to this point, all I established is that s theta is, I can write in this form. Notice how my sleight of hand here is that the expected value of the score is 0. And so the expected value of this whole thing, w prime theta, this, is 0. So you can show that the expected value of t minus c prime theta over c theta, w prime theta is 0, right? I throw out this w prime here because it doesn't matter. You can multiply it on both sides. And hence, the expectation of t is exactly this thing, this horrible expression, right? So everything's okay. So I actually didn't cheat here. It turns out that, so if you wanted to do this in more methodically, you would say, you kind of stop with this blue line here, and you'd say, okay, so S is this. Therefore, the expected value of t is this mess. We're calling that tau of theta, and so therefore we can do the factorization. So we're good. Okay. That is it on the Kramer-Rao lower bounds. If you hated that, that's pretty much it. We're gonna generalize our method. We're going to talk about another approach to finding best estimators. And what I think is best use of our kind of time remaining in this lecture is to talk about iterated expectation and conditional expectation. So let's just put some double bar here. Let's say done with CRLB. So done with the score, done with information, done with Kramer row, done with attainability, all of this fun stuff. Let's approach this problem. We're going to approach this problem in the next couple lectures from a different viewpoint, how to find the best estimator. And it's going to rely on conditional expectation. And so we're going to spend the last part of this lecture on a review of condition / iterated expectation. Okay. So let's review. So if you take in 451 with me, this is in Dr. Lemus's book, in his probability book. This would be section 6.3. So just for a quick review of these things, right? If I have a bivariate random variable, let's call it x and y, and they have, bivariate random variables, or two random variables, have a joint distribution, let's call it f of x, y, and marginals, which I'm going to call fx and fy, right? And I'm abusing notation by reusing f. I think it's clear though. And the conditional distribution of x given y is equal to some little value. So you have to specify, we're given that y is not random now, it's fixed at some value little y. And given that y this is supposed to be my random variable, capital Y, is fixed at some value little y, we can talk about the conditional distribution of x and y, which is typically denoted f of x bar y. This is the easiest way to denote this. And this just has the formula of the joint over the marginal of y, fxy over fy, right? Now, another way, let me just say, we can think of x given y is little y as a univariate random variable, right? So my formula up here, you can think of it, you tend to think of it just as a function of x. It's just some univariate PDF. If I fix little y at some value, this thing is just a function of x, and it has some formula, but it's just a univariate PDF, and it is exactly a univariate PDF. And this quantity, which is typically how we denote the conditional random variable of x given y, we can think of as a univariate random variable. If you give me a little y, x given y is equal to little y is a univariate random variable. It's different than x itself. It's different than the joint of x and y, which is bivariate. It's some other univariate random variable. And because, you could call it z, right? You could call it whatever. It has, because it's just some univariate random variable, it has fancy notation, x bar y, but it's just, we could just call it z. Let's just call it z. It's some random variable z. And if you don't like the x bar y is little y, right? Just call it z. Z has a distribution, has a PDF or PMF, which is given to us as f of x bar y. But it has other things. Z has an expectation, which, so you could say the expected value of z, right? Which often it would be denoted the expected value of x bar y is little y. But this is just fancy notation for the expected value of a certain univariate random variable that has fx bar y as its PDF. So we actually really haven't done anything too complicated here. You know, this conditional expectation is just the expectation of a certain random variable we've made with this PDF, right? If I were just to give you that as a PDF and say that's the PDF of a univariate random variable, you'd say, yeah, great, okay, and you can calculate this expectation and all this good stuff, right? And that's all we're doing, right? The formula for this would be, you know, x times its PDF. The PDF of this thing is x bar y, and you integrate dx, right? Not too bad. Notice how, though, if y, little y changes, so does my univariate random variable x given y little y, right? So this is why people get uncomfortable, because I get a different random variable for each value of little y. And so there's that, and hence, if I were to say calculate, you know, if I just look at the expected value of some univariate random variable, maybe the univariate random variable is x given y is equal to little y, this thing is just a number. But it's a number that changes depending on little y. We have a name for that, i.e. a function. That's what we call numbers that change depending on other numbers. We call them functions, right? So we could call that thing g of little y. So we could make a little function g of little y, and if you give me my value of little y, I'm going to give you the conditional expectation of x given y is at that little y. And g is just some real valued function. You take in the value of little y, and it spits out the conditional expectation. Nothing too fancy. What gets fancy is when you say, so g is a function. I can look at functions of random variables. What if I plug my random variable y into g? So we say we plug my random variable y into g to get g of y. Now, when you talk about that in 451, that's okay. Nothing too scary. It's just now our g is some very particular g. So, you know, what we'd like, you know, typically you'd say g of y, you know, if g of y were y squared, you know, if g of y were, if g of little y were y squared, you would say g of capital Y is y squared. Now, g of little y is the expected value of x given y is equal to little y. So instead of plugging in little y, we're tempted to plug in capital Y. We don't like this notation. This notation is awkward. And so instead we use this. We say expected value of x given y, like that. But notice that g is just some function, y is a random variable, so g of y is another random variable, and our notation for g of y, because that's really cumbersome to write, is expected value of x given y, and this is a random variable. Basically, an even easier way is that expected value of x given y is this thing, whatever this quantity is, but treat little y as random. E.g., if expected value of x given y is little y is y squared, then expected value of x given capital Y is capital Y squared. That's all it is, but you just have to remember that the second version, the first version is a number, and the second version is a random variable. So let me just write that out real quick. Let me just say punchline is that this thing is a number, and this thing, expected of x given y, is basically the above thing, but we treat the y as random also, a random variable. And in the kind of minute I have left here, and we'll talk about this next time, we have this theorem called iterated expectation. There are multiple names, so that's the name I typically use, which says that if I want to get the expected value of x alone, I can look at the expected value of the expected value, so I iterate my expectation of, in the inner I look at the expected of x given y, and this outer expectation is with respect to y. So iterated expectation says if I know something about the conditional of x given y and something about y, I can calculate the conditional, the marginal expectation of x. We'll leave it there, and next time we'll start off with a review of iterated expectation, and then launch into how that relates to our pursuit of the best estimators. But yeah, we will stop it there.